Hello and welcome everyone to week 6 of QM. I hope that you guys were able to do as well as you would have hoped in the quiz. But now that the quiz is over, let's focus on the next teaching weeks that we have. And the topic for this week is a continuation of probability from the last teaching week that we had. And namely, we're going to talk about probability distributions, specifically these four distributions that we have. And we're also going to be talking about expected value within the context of these probability distributions. So let's start with the normal distribution. It is the most common and the most famous of all of these distributions. It's used very widely in many spheres and fields, right? It's characterized by this bell shape that you have here, so this nice looking smooth curve. One of the properties or one of the characteristics of a normal distribution is that its mean is the same as its median, which is also equal to its mode. So as you can see here, it's nicely shaped and very symmetrical. In fact, if I were to cut the normal distribution at its center, throw away one part of it, and mirror the other, I would still have the same original distribution that I started with. And normal distribution is found everywhere in a variety of things that people observe in the real world, and many things are normally distributed. Last thing, with regards to the shape of a normal distribution, is that it has zero skewness. Now, what do I mean by skewness? Um, Look at these two other types of distributions that you have. So the one here, the first one, has a positive skew, also known as skew to the right. So if you could think of this as a symmetrical distribution like this over here, what you have are a significant amount of outliers right over here, that is really large numbers. And what they serve to do is they are skewing this distribution to its right, so it's making it a bit tilted towards the right hand side. If you look at the next distribution that you have over here, this one has a negative skew. So again, if you would think of this as being a symmetric distribution, what you have are a large number of outliers that are much smaller than the mean, and what that serves to do is skew or tilt this probability distribution towards the left. The normal distribution, like I said, has a lot of well-known properties, but the most commonly used one is this one over here. So let's say you have a random variable or some amount of observations, and you have found its mean, which is over here. Then if you were to add and subtract one standard deviation from it, which is this part over here, then 68% of your data is going to be contained within it. So if you have 100 observations, then you expect 68 of those observations to lie within this small range. Likewise, if I were to add two and subtract two standard deviations from the mean, then this contains a majority portion of my data, so specifically 95%. And if I were to go ahead and add and subtract three standard deviations from the mean, then I have almost all of the data sets that I am looking at. Within the family of normal distributions, we have what is known as a standard normal distribution. This one specifically has a mean of 0 and a variance or a standard deviation of 1. It's inconsequential which one we're talking about, because the square of 1 is 1 and the square root of 1 is also 1. Lastly, one of the reasons of the popularity of the normal distribution is the central limit theorem, which states that averages of a series of samples or any data set that you have that is drawn from any other distribution. So the dataset itself does not have to be normally distributed, but if we are talking about its, for example, its mean, then the central limit theorem says the mean of this dataset. We talked about mean in our previous weeks, but let's revisit it again, but from a different viewpoint. So here we are looking at it from a probabilistic standpoint. So the expected value for any distribution is the average value from repeated observations that we get when we're sampling from this particular distribution. So under a normal distribution, the expected value of that random variable is going to be its mean, or in other words, its arithmetic average. Then let's look at variance again, right? Variance is the expected value of the square distances of any random variable from its mean, or in other words, its average square distance from its mean. Another approach to finding this variance is, first of all, taking the average squared numbers of the observations that we have, and then subtracting from that the square of the average, right? Which again in here it just states that variance is the average of the squares of these numbers minus the square of the average. Variance is also known as the second central moment. So a moment is just the expected value of a random variable raised to an integer exponent. So all the observations that you have raised to the power 1, that is itself, is known as the first moment or the mean. Variance is the second moment. Notice that in variance we are talking about, or we're mostly interested in centralized moments. That is, we are not looking at the moment that is centered around 0, but that is centered around its first moment or its mean. Lastly, up until now, the formula that you had for variance is the population variance. That is, if we were interested in knowing the variance for any particular data set, then we would have to sample or get a record of all of the observations that could ever be possible for that particular thing that we're trying to study. But usually that is not going to be feasible, either because of a time constraint or a cost constraint. So what we do is we take a small sample from the whole population that we have. So for example, if we wanted to know the average height of people in Uzbekistan, we cannot go around and ask each and every single one of them. It is infeasible with regards to a time and cost perspective. So what we do is we ask a random small number of, relatively speaking, a small number of people, and then if we wanted to calculate the variance for the population, what we'd have to do is take the sum of the square deviations that I had, which is right over here, and then I would divide it not by n, but by n minus 1. And here this sample variance formula is the estimator for the true variance of the whole population. If you were to use the population variance on a sample, it would underestimate the actual size of your variance. And this n minus 1 that you see over here is known as Bessel's correction. You don't necessarily need to know it for QM, but if you're interested in knowing why exactly it's n minus 1, this is a starting point for further searches and studies. Right, so that was it for the normal distribution. Now let's look at another distribution. This one here is the uniform distribution. It is probably one of the simplest distributions that there ever is. It is just a random variable that has the same probability of each of its values occurring. So for example, consider throwing a die. right? Each of its faces are equally likely. So there's an equal probability of you throwing a 1 or a 2 or a 3 or a 4 and etc. Under a uniform distribution, the expected value is just going to be the smallest number that could be possible plus the largest number divided by 2. So let's look at this example that we have over here, which is again rolling the dice. Um, the number on each of these faces are equally likely, so the probability for throwing a die would be, as you can see over here. So for example, the probability of throwing a 6 is approximately 16%, which is over here, and the probability of the other faces showing is also going to be the same. In this case, the expected value or the average observation that I am expected to observe from here is just going to be a plus b over 2. That's going to be 1 plus 6 divided by 2. So in that case, it's going to equal to 3.5. So right here, you have a task to do for yourself. So in this case, consider a 4-sided die. So usually a die would be 6-sided, but let's say this one has 4 sides. I want you to stop this video right now and calculate what the expected value from throwing such a die would be. Then let's move on to talking about yet another distribution. This one is known as the Bernoulli distribution, and the Bernoulli distribution arises from uh, a random sampling or a random experiment that only has 2 outcomes, A and B, and there is no possibility for another third outcome, right? So we would call one of these outcomes a success. That is the event that we are interested in. We would label it as a success, also denoted by x equals 1, and the other outcome as just a failure, also denoted as x equals 0. Then the probability of a success would be written as pi. The probability of a failure would be exactly the opposite of that. So that's going to be 1 minus pi. And notice that the sum of these two events must equal to 1. And as you can see in here, that is the case. So the probability of a failure here is going to be this one over here, 1 minus pi. The probability of the thing that we are interested in is going to be pi over here. If we add up both of these probabilities, it should equal to 1. So for example, let's look at tossing a coin. So let's say we are interested in a tail showing up. That would be our success, and the failure in this regard would be throwing a heads. Or for example, passing or failing in an exam, defaulting a loan, etc. Right? So like I said, a success is just the event that we are trying to study. A Bernoulli experiment has a mean equal to the probability of a success, right? And the variance that is just the product of both of those probabilities that we have. So for example, consider tossing a coin again, right? So the probability, what is the probability of landing heads, right? So since let's assume that this is a fair coin, in that case, probability of landing a head or a tail is equally likely. So in this case, that's just going to be 50% or 0.5. How about its variance? Like I said, the variance is just probability of success multiplied by a probability of a failure. So in this case, the variance is just going to be 0.5 squared, or in other words, just 0.25 or 25% squared. So again, consider this task or this example over here in which you are throwing a fair die. So now what I would like you to do is pause this video and calculate the probability of getting a 5 or a 6. So in this case, if you have a 5 or a 6, that is your success. If you get any other number, that is a failure, right? So what's going to be the probability of a success in this instance? And then I also want you to calculate the variance. That is, once you have calculated the probability of a success, you multiply it by the complement of that probability to find the variance. Make sure you stop the video and try to do this. But anyway, let's move on. Right? The final distribution that we're going to be looking at this week is known as the binomial distribution. A binomial distribution arises when you look at a Bernoulli experiment and you keep repeating it some number of times. One other thing to note is that each Bernoulli experiment or trial must be independent of all the other trials. So, for example, when you're tossing a coin, if it comes up heads in your first try, that does not affect the probability of you having heads or tails in your second throw, and etc. And since in our Bernoulli experiments that we are the n series of Bernoulli experiments that we're doing, since they're independent, probability of success P remains constant and does not change. Like I said, the probability of getting a tail is the same whether it's our first time that we're tossing it or the 10th time that we are tossing the coin. So in a binomial experiment, we are interested in the total number of successes in these n number of trials, that is, the x number of successes in an n trial. So in that case, the binomial random variable x is just going to be the sum of these independent Bernoulli experiments. So the result of each of these n identical trials must be one of two mutually exclusive and collectively exhaustive outcomes. By mutually exclusive, it means that the probability of a success does not have some probability of a failure inside it, and the probability of a failure does not have some probability of a success in it. That means that if something is a success, it cannot also be a failure. If something is a failure, it cannot also be a success at the same time. By collectively exhaustive, what I mean is anything could be either a success or a failure, but no other third thing. So we don't have any other thing. So the success and the failure completely explains all of the sample space that I have. So when we look at tossing a coin, if it lands a head, that does not mean that it has landed a tail as well. That means it's mutually exclusive and it's collectively exhaustive. That is, either I could have a head or a tail, but I don't have any other outcome. So for a discrete random variable x, x is the number of successes in n number of trials. So if we are interested in 5 heads in 15 tosses, then 15 would be our n and 5 would be our x. Or if we look at, for example, light bulbs and we want to know which one of these are defective, or the probability of getting a defective light bulb, then in this case n would be 10 would be our n and 3 would be our x. So notice that a success does not have to be something that is favorable or something that is good or nice. It's just whatever it is that we are trying to study in our experiment. So remember that a binomial distribution is just an n series of Bernoulli experiments. That means that since the expected value for a Bernoulli random variable is just pi, if we were to repeat it n number of times, then the binomial distribution's expected value would just be n multiplied by pi. Likewise, it's very similar for variance. So the variance for a Bernoulli experiment was just this one over here, so pi multiplied by 1 minus pi. If we repeat it n times, that's going to be n multiplied by the Bernoulli variance to get the binomial variance. And as a result, its standard deviation is just going to be the square root of that. Notice that in a binomial distribution, the only two parameters that we're interested in are n and pi. And the probability distribution for a binomial process is given by this following formula. So the probability of us getting x successes is equal to n combination x multiplied by the probability of the success x number of times multiplied by the probability of failure the rest of the times. Let's look at an example so that you guys can understand it much clearer. So let's consider a coin that is tossed 10 times. I want to know what's the probability of observing exactly 3 heads. So in this case, my x is going to be equal to 3, n in this case is 10, and pi is equal to 0.5. So let me write that down. So x is equal to 3, n is equal to 10, right? And our probability is just equal to 0.5. So the first thing that I'll have to do is find 10 combination 3, right? So remember from previous week, it was that big formula using factorials, and 10 combination 3 gives me 120. Then I am interested in having 3 heads, so the probability of success of 1 head is going to be 0.5. I'm interested in 3 of those, so I'll have to multiply it by itself 3 times. That's the probability of me getting 3 heads. Then I multiply it by the probability of a failure. In this case, it's equal to itself, equal to the probability of a head. So that's going to be 0.5. Then since I have 10 trials that I need to do and 3 of them I want them to be heads, that means that the rest of the 7 should be tails or failures. So that means I'll have to multiply it by itself 7 times. If I do that, I get this number over here. Then if I multiply all these numbers together, I will get 0.11 or 11%, which is the probability of observing exactly 3 heads. Now, here is a task that I would like you to do right now. So pause this video, look at this question, and try to solve it. Right, so in this task, it says, a student has 10 exams coming up. She has a 90% chance of passing each exam. What is the probability of passing exactly 8 exams and failing exactly 2? So I want you to do this task on your own right now, and we're going to be I'm going to be posting the solutions for this later in the week. One last thing to note about a binomial distribution is that as the number of Bernoulli tries that I do keeps increasing, and provided that the probability remains constant, then this binomial distribution starts to become closer and closer. That is, it starts to converge closer to the normal distribution. As you can see over here in this chart, so if I have 20 Bernoulli trials, then it looks like that blue curve over here, and as I keep increasing the number of trials that I do, this Bernoulli distribution approaches the normal distribution. That is it for this week. So this week we discussed the 4 probability distributions: the normal, the uniform, the Bernoulli, and the binomial. And we also looked at their expected values, that is their mean and their variances. So see you guys next week.